Well, hello, and guess what we're doing today? Rotation transformations. And as you can see, I just went ahead and made a big mess. Maybe you could make some sense out of this. These show the three big rotations. I'm going to call this the pre-image right here. Doesn't really matter. For instance, if I called this A, this would be a 90-degree rotation, 180 and 270. I'm going to call this A. And these will be the images of A under, this is like A prime under a 90-degree rotation, A prime under a 180-degree rotation, A prime under a 270-degree rotation. I use different color lines here so you can see which point is going where, and colors of the same line should be perpendicular. I didn't draw those in because it's already a little too crowded. But you take a look at the blue line, for instance. The point 41, as we rotate it 90 degrees, becomes the point minus 1,4. And if we draw our line from the origin to that point, it should be perpendicular to the original line. It will also have exactly the same length. That's pretty easy to see. Use your distance formula. The square root of 4 squared plus 1 squared. Well, over here, completely different. That's 1 squared plus 4 squared. No difference. Same thing here. This is the point 2, 1. It's a little hard to see, but this goes to the point minus 1, 2. And the point 3, 3 goes to minus 3, 3. And there's some rules for that. There they are. For a 90-degree rotation, we switch. Well, that kind of looks like what happened, doesn't it? We went from 4, 1. Oh, can't see it. To minus 1, 4. See, we switch. And then the x-coordinate becomes negative. So we swap x and y and take the negative here. Did that off swapping 3, 3 obviously has no effect. Swapping 2, 1 becomes 1, 2, and you make the 1 negative, so it's minus 1, 2. For the 180-degree rotation, well, that's just a straight line, right? And lines of the same color should form a straight line. So here we go from 4, 1 to minus 4, minus 1. Do we have a rule for that? Yeah, there it is. We leave them the same. We just take the negative of each one. So our coordinates become negative A, negative B, and that's what we have here. Like this is minus 3, minus 3, and that was 3, 3 here, minus 3, minus 3, 2, 1, minus 2, minus 1. That's pretty easy. And this one here, well, you can probably guess what we did here. We left them swapped them again, just like we did for the 90-degree rotation, but now the second coordinate, the y-coordinate, becomes negative. That is the y-coordinate after the swap. This was originally the x-coordinate, of course. We swapped them, and then the second coordinate becomes negative. Here, for 90 degrees, we swap them and take the negative of the first coordinate. Here we do the same thing, we swap them, but we take the negative of the second coordinate. And for this one, we don't swap anything, we just take the negative of each coordinate. It's really pretty easy. And when we do that, this is what we get, these three different rotations here. And there's one very important thing about these rotation transformations, just like the translations and reflections. Rotations are also isometries. In other words, the side lengths, the areas, the perimeters, those all remain unchanged. In fact, the sides and angles remain unchanged. You end up with exactly the same shape, not just to scale, but at the same size. In other words, a 1-to-1 scale. And like I say, I think the easiest way to see that is, especially later on when we have more formulas, but we have some formulas already for area, perimeter. Where does the location of the object come in? It doesn't. So we can move it all we want. It's not going to change, as long as it's a rigid motion. We're going to see some transformations in a section or two that do actually change the shape. And we've already seen some of those where they change the size. And that's probably about all we're going to change in this class. You can do lots of things with transformations. You could, if you not concerned about maintaining congruence, you can turn a triangle into a circle with the right transformation. It will be a very complicated transformation, and beyond what we're going to do in this class. And I think I've pointed out in previous videos that it doesn't matter whether when we're using coordinates anyway, it doesn't matter whether we perform the transformation on the object or on the coordinates. In other words, I can take this triangle and rotate it 90 degrees about the origin. And we already know what's going to happen. We saw it earlier. It's going to look like this triangle over here, because we've kept the coordinate systems right where they are. Suppose I leave the triangle and rotate the coordinate system. Well, if I rotate the coordinates instead of the object, where do I end up? Well, I just did that, and look at where we are here. If you can read this, maybe if you turn your head sideways, it's easier. We've got -1, 2, -1, 4, and -3, 3. Well, what did we have before? -1, 2, -1, 4, and -3, 3. We could rotate this triangle over this way, and see this 3, 3 rotates all the way around. It becomes this point here. Or we can rotate the coordinates and end up with exactly the same thing. The ability to move coordinates is much more important than the ability to move triangles around. We're using triangles as an example. Later on we could use other polygons, but moving polygons around, rotating them, reflecting them, is not nearly as important as pointing out the invariance of these objects under coordinate transformations. And that's in fact what we're doing. When we transform the object, we could just as easily say that we're leaving the object alone and transforming the coordinates. I think I did that with the reflection when I made a reference to the Celsius scale. I think I referred to him as some guy. Well, obviously the guy was Celsius. It's named after the guy. He started out with the backwards, what we would call backwards, because as temperature went up, the numbers became more and more negative. So the boiling point was like -100. That goes back to when they thought that cold was the operative quantity, not heat. And heat was just the removal of cold, in other words. So when you made water boil, you didn't add heat to it, you removed cold from it, then it started to boil. So his negative numbers made a little bit of sense if you look at it that way. But they didn't last long. That's why you've never heard of the negative Celsius scale, because very quickly scientists reversed it. We also showed that shifting coordinates around is irrelevant to the object, and now we can see that rotating the coordinates also has no effect on the actual object. And this is very important in physics, where we have things that are called invariant. Invariance, well, half the job of physics is finding things that are invariant under particular conditions. And coordinates are important conditions. So things that are coordinate invariant, like the size of your property, that's important. I mean, if you've got 1.5 acres when you measure it, but if you measure it with the origin back at the city center, you've only got 1.3 acres. Well, you've got a serious complaint. It's not supposed to work that way. Now let's go ahead and work some problems. This is actually, now these rotations are actually fairly simple as long as we're rotating about the origin, and that's pretty much what we'll be doing, I think. In other words, you're not going to have any trouble at all with this section. With this, we don't even need to draw. When we were translating, it was easy to count the number of units. We had to shift something left or right or up or down and then do it. And it's not so easy with this. I think it's easier to just stick with the coordinate rules, which I went ahead and wrote in here. This is the rule for 90 degrees. There's one for 180 and 270. They're not that hard to remember. Well, first we need to know what the coordinates of the original object, the pre-image, are. So these are the coordinates. I think I got this right. Let's see, 2, 1, 2, 3, 4. So what do we do now? All we have to do is apply our coordinate rule. It's pretty easy. We can start over here at A, our new A anyway. What should we call it? I got an idea. Let's call it A prime. That's a good label for an image. The pre-image is A, the image is A prime. So what do? We have to swap the 2 and the 3. Well, 2 and the minus 3, pardon me. The 2 becomes a negative 2. And the x-coordinate, we just switch position, but don't change the sign. So we get minus 2, minus 3. What about B prime? We swap them and negate the first one. So we get minus 4, 2. And here at C prime, again we swap, and the first part we take the negative, the second we leave alone, and these are our coordinates for a rotation of 90 degrees about the origin. We could roughly guess where that would be. Let's see here. And if I sketch in the points to sort of guess at where this one would be, this is minus 2. Oops. This down here is about minus 2, minus 3. This point up here, minus 1, 3. This is this point here. I draw it, but it's getting a little crowded in here. Let's see here. Minus 1, 3. That's that point right here. Now, as you can see, this here, C prime is the image of this point over here. We've rotated it 90 degrees and it wound up here. Same thing with this. We took B. If we drew a line here, it'd get too crowded if I did that, and rotated it 90 degrees, we would have this line here. And same thing with A. Put a line from the origin out to point A, and then to A prime. That one might be a little bit shaky because I only guessed at where point minus 2, minus 3 would be. The other two will look much more accurate. And this one, it definitely looks like a right angle to me. Well, this one's Pretty easy, I think. First, let's remember our quadrants. Remember, we go counterclockwise. So this, between here and here, this quarter, that's the first quadrant, the second quadrant, third quadrant, and fourth quadrant. Well, what do you think? If we draw this, if we sketch in a line from here to the origin and rotate it 180 degrees, where's it going to go? Right about there somewhere, right? Looks like the third quadrant to me. This was pretty simple. Well, here's one that's kind of interesting. It's tempting to start worrying about the rotation here. Like, what are our new coordinates, or how do we perform this rotation? And what the heck is point P? Well, that's not really important. The important part of this problem is remembering that a rotation is an isometry. It's a congruent transformation. Congruence transformation. It's a rigid motion. Any one of those three will work, and all that adds up to is we don't change the actual object. So everything's the same. The sides, the lengths stay the same, and the angles stay the same. Lengths and angles are all preserved in an isometry, or a congruence, or a rigid motion. Any one of those. So what does that mean? Well, we just have to figure out corresponding sides. Well, I think that 3y, this side here, corresponds to this one. This side here corresponds to this side. So we can write that x equals 5 from this. And we also have that 3y equals x plus 7. And they asked us to find y. Well, okay then. Kind of looks like 3y would be 5 plus 7, or 12. And that means y equals 4. I hope that's one of the answers up here. Yeah, here it is. As I say, the important part of this problem wasn't so much figuring out how to rotate it, but as remembering that rotations don't change the object. Lengths and angles stay the same. That's why we can say that 3y equals this, x plus 7, and we can say that x equals 5. Now in this one we're given the vertices of a rectangle, and they want to know which one of these translations will place one of these points at the origin. That's what these are. These are the vertices here. So one of these points is going to end up at the point 0, 0. Put it another way, one of these points, we don't know which one, we'll just say xy, is going to go to 0, 0. But we don't know which transformation will do that yet. Let's see, suppose we go right 4 units and down to, well, gee, that's going to put us even farther away from the origin, isn't it? 4, 0 will become 8, 0. And then down. So it will become 8 minus 2. And it's not going to get us anywhere near the origin, is it? A rotation of 180 degrees about the origin. Well, that's just going to make everything the negative of what it was before. This will become minus 4 minus 0, which of course is just 0. This will become minus 4 minus 2, and on down the line. It's just going to move everything here. Well, just think of it as a rotation. Reflection in the line x equals 4. Well, now we're talking about something here. We might have something. Let's take a look at the line x equals 4. Remember how we reflect things about a line however far it is away from the line on one side, it has to be the same distance on the other side. For instance, here we have the point 70, which is 4 units to the right of the line x equals 4. So we have to place it 40 units to the left. And that puts it right about here, doesn't it? So 70 will go to the point 0, 0. Well, that's what we were looking for, wasn't it? Which image? And this isn't a problem that allows for more than one choice. Otherwise, we might have to check D. Maybe the answer is C and D. But this is one of those multiple choice problems that only has one answer. And since we found one and they only asked us to find one, we don't have to check to see if there are any more. Sometimes you have to check and see if you made a mistake or if the answer makes sense. But here, I don't see where there's any reason to even check the next one, because we just found one, and that's all they asked for. And it was actually pretty easy. When you think about flipping this over, you know what a reflection is. If you were to hold a mirror right here, you would see an image of this. Now here we have an interesting problem that involves rotating a line about the origin. We're given the equation of the line, y equals 2x minus 3. We're going to rotate it, find the equation for the new rotated line, and then talk about what we just did. So, easiest way, let's see, we're going to rotate this 90 degrees. Just pick 2 points. Remember, 2 points define a line. And we can also use that to find the equation of the line later on. So a 90-degree rotation, say for the point, this is the point 3/2, 0. That's this point right here. I've rewritten the rules up here just as a reminder of what we need to do. So the point 3/2, 0 goes to, well, negative 0, which is still just 0. And 3/2. 0, 3/2. And this point, which is 0, 3/2. Now we have, we can take advantage of some things here. For instance, since the line crosses the axes, we plot the 2 points where it crosses. And it's very easy to rotate these axes 90 degrees, isn't it? I mean, we can use the rules, of course, just like I've written up here, or we can visually recognize that a 90-degree rotation of one axis just puts us right onto the other axis, the one right next to it. Well, our next 90-degree rotation is going to have to be perpendicular to this blue line here, just like the blue line is perpendicular to our original line. That's what it means to rotate 90 degrees. So our only real question is, where do we place this line? We know it has to be here somewhere. We know we've got the slope right. It has to be perpendicular to the blue line and parallel to the other, whatever color that is, reddish brown. But where do we place it? Right here. Well, let's see here. If we start with our original one, what would our new coordinates be for the two 90-degree rotations, which is just the same as a 180-degree rotation, minus a minus b. So we have minus 3/2, 0. Well, there's minus 3/2, and there's 0. Down here, I mean. What about this point here? Well, 180-degree rotation, what does that do? That brings it right up to here. Or we could apply this and get 0, 3. Negative 0 is still 0. Negative minus 3 is 3. So we get these 2 points on our line, and now we can correctly position it. This is our 180-degree rotation of this line about the origin. You would think that a 180-degree rotation of a line would just give you the same line back again, right? Well, not quite. If we were to rotate it about some line, if we were to rotate about a point on the line, a 180-degree rotation would just give us back the same line. But we're rotating about the origin here, so that means the whole line has to move, and it changes orientation as well, because every single point has to swing around 90 degrees. This point swings around 90 degrees to here. This one swings 90 to here. And then we do it again. This one swings 90 down to here. This one swings 90 up to here. So you want to take a wild guess at where this is going to go if we swing it 90 degrees down? Yeah, I think that's where it's going to cross the y-axis. But if we check right here, this point right here should go to 0. Okay, there's where x equals 0. And the second coordinate, the y-coordinate, becomes the negative of the original x-coordinate, which is minus 3/2, which puts us right here. Oh, well, that's pretty much what I said, isn't it? And if we rotate this one down, or another 90 degrees counterclockwise, this point's going to end up right here, and we have another line through here. So our last line looks like this. Well, now we know what they look like. It doesn't tell us much about what the equations are going to be, does it? Although it gives us a way to figure out what the equation's going to be. For instance, the slope of this line is perpendicular to this one. So we can just, that has to be this line has to be the negative reciprocal of this one. Well, this one has a slope of 2. It's right there. The part in front of the x, that's the slope. Also known as the coefficient of x. So the slope for this perpendicular line must be minus 1/2. Remember, it's the negative reciprocal. So we get minus 1/2 x plus, well, what's the y-intercept? Right there. It's 3/2. We can just read this one right off the graph. So that's our new equation for the line. What about, this is our, let's call this y sub 90. That's the equation for our line that's been rotated 90 degrees. What about the next line? Well, it's perpendicular to this. That's one way to look at it. It's a negative reciprocal of the slope of the blue line, or it has exactly the same slope as the reddish-brown line. Look at it either way, you get 2x. The slope is 2, just like for the original line, but what's the y-intercept for this one? Pardon me, the y-intercept is up here. It's 3. And what is that? That's y sub 180. So all we've really done is change the plus 3 to a minus 3. Okay. What about y sub 270? what's that going to look like? Well, it has to have the same slope as this other blue line, doesn't it? It's perpendicular to both of these, so we're back to minus 1/2. And what's the y-intercept? Minus 3/2. What about 360? Well, gee whiz. 360-degree rotation is the same. Well, think of it as a 90-degree rotation from 270. Here's 270. If we rotate this point up 90 degrees, we end up right here. We rotate this point down here 90 degrees, and we end up right here, which puts us right back at our original line. Which makes sense because, as you know, 360 degrees in a circle is just the first full circle. When you get to 360 degrees, you're just right back where you started. And that's what happens with rotational transformations also. When you rotate something 360 degrees, you just end up with what you started with. So we get 2x minus 3. And in the end, I think they ask you to, would this be true, what we're doing, would that work for any line? In other words, as we rotate at 90 degrees, could we just substitute the negative inverse for the coefficient of x and replace the previous x-intercept with the y? Is that what I'm trying to say? In other words, the new y-intercept becomes the old x-intercept, and vice versa, if that helps. In other words, for the original line, which was this one here, the x-intercept was 3/2. Rotate at 90 degrees, that becomes the y-intercept. We rotate at 90 degrees again, it becomes the x-intercept. So the x and y-intercepts are just swapping back and forth. The coefficients in front of the x are just going back and forth between negative reciprocals. They're just going to flip back and forth between 2 and minus 1/2. And the intercepts, as I say, will just keep flipping. The y-intercept is now the old x-intercept. And if we do it again, the y-intercept becomes the previous x-intercept. In other words, here's our line. We rotate this 90 degrees, and what happens? The y-intercept becomes the x-intercept. The x-intercept becomes the y-intercept. And yes, that will work for any line. There's nothing magical about this first line that we drew here. No matter where we place this line, rotations of 90, 180, 270, and then 360 will produce the same pattern, I guess you could say. Okay, they say they provided a small graph at the right. I went ahead and redid it. This is the original one. If it's not obvious, this is the x squared plus 1. This is what you get when you replace x with y. So technically you would write y equals x squared plus 1. That's this here. This one here, well, we reverse everything and get that x equals y squared plus 1. Well, we didn't know that replacing x and y was going to be a rotation with respect to an equation, although that is one of our but this certainly looks like a rotation. It looks like we rotated, let's take the point 0, 1 all the way to the point 1, 0, which is, if we go from 0 to 1, or 0,1 to the 0.10. Well, that's kind of like going from AB to B minus A, right? Because -0 is still just 0. So it makes sense. I think you could just as easily think of it as a 90-degree rotation in the wrong direction. In other words, -90 degrees. Counterclockwise is what we call positive. So going from the red to here, that's 270 degrees. Or you could say going from here to here is 90 degrees. Or going from the red to blue, that's minus 90 degrees. And that was the question down here. What is the angle of rotation? Are the image and the pre-image both functions? Well, this is a function. For every y, there is exactly one x coordinate. Pardon me, for every x, there is exactly one y coordinate. Don't let me get by with saying things like that. For every x, there is one y coordinate. Remember, it's a function of x, so to be a function, the result over here has to be unique. Otherwise, you just get a big mess. You don't know which one of these you're referring to. If x squared plus 1 could be different things. But over here, well, if we solve for y, I think what we get is that, put it down here. Y equals square root of x minus 1. But it's really the plus or positive or negative square root of x minus 1. If we restrict this to the positive square root, we have this upper line here. That would be a function. If we restrict it to negative square root of x minus 1, that gives us this line down here. And why does it stop here at 1? What happens when x is less than 1, like when x is 0? Well, then we get the square root of minus 1. Where are we going to graph that? We don't have that number yet. It doesn't exist for us. So we have to stop right here. See, with this function, x went to plus infinity, minus infinity, no problem. This y was defined over the entire number line. But when we do it this way, no. As soon as x becomes less than 1, we're out of luck. There's nothing we can do. And the easy way to spot that this isn't a function, just draw yourself a vertical line. Well, gee whiz. If I ever draw a straight line freehand, send me $1 million check. Don't worry, you'll never have to write the check. It'll never happen. Draw yourself a line, perpendicular, vertical line through the x-axis. If the function crosses the line more than once, that's not a function. It can only cross once. That's the easiest way to, if you've got a graph to look at, just draw yourself a vertical line. If it crosses the line twice, it's not a function. Well, that was fun, and that's about it.